Great. Welcome, everyone. Hopefully, you all caught either Matt or Peter's keynote, heard a little bit about TRN2, and you wanted to learn more, because that's why we're here, to learn about TRN2. I'm Joe Sinertia. I'm a senior product manager for AWS AI chips, and I'm super excited about today's session, because we have two experts here with us. We have Ron, who's a senior principal engineer and the chief architect of our AWS AI chips, and we have James, who's a distinguished engineer of compute at Anthropic, one of the leading AI founding labs. And so, just a quick overview of what we're going to cover today. So I'll quickly walk through some of the AI trends, the AWS AI infrastructure, and then I'll have Ron come up on stage, talk about how we built Trainium2, and think about building silicon. And then James will come on to talk a little bit about how they think about scaling frontier models, how Anthropic thinks about scaling frontier models, as well as their bet on Trainium. So let's get started. So there's a lot of hype around generative AI. Sometimes you hear artificial general intelligence, sometimes deep learning or machine learning. But why is it getting so much hype? Well, I think when we look at Andy's message in his 2023 shareholder letter, he covers it pretty well. AI, generative AI or AI, has the capability to transform, to be a technological transformation as big as the internet. But what exactly does that mean? Well, when you look at AI and the tasks that it's already completing, it's already a broad range of tasks, and it's taking tasks that took months down to days or even hours. And when you have the capability to then magnify productivity by 10x, 100x, or even 1,000x, that creates this new wave of technology transformation that Andy's talking about. And I think we're really excited about what you all will build with the AI capabilities that we're working on. And that's also why we've been innovating across our entire AWS generative AI stack. So starting at the top, you have applications to boost productivity with Amazon Q, which gives you the ability to write code, generate content, even manage your AWS resources. Then if you want to get started with some of the large language models, we have tools with Amazon Bedrock so that you can work on and work with the leading frontier, some models from the leading frontier labs, such as Anthropic, Cohere, AI21, even the recently announced Amazon Nova. And so then when you move all the way to the bottom stack, powering the top, and this is the one I'm most excited about, and hopefully you all are, because this is a compute session, it's the infrastructure, where we have built secure, resilient, performant, and cost-effective options for your AI workloads. And so let's take a little bit closer look at how we think about infrastructure at AWS. So whenever you hear infrastructure, a lot of times you think hardware, compute, and that's super important. But at AWS, it's much broader than that. We're working with the open source libraries like PyTorch and JAX to make sure that that works well with the underlying hardware. We're also a founding member of OpenXLA so that we can make sure that the open source frameworks that you're using works on any of the hardware that we have available. And then in the middle, we have orchestration and management. And these range from self-managed tools like EKS, where you can scale up to thousands and thousands of nodes on your own. Or for a more managed experience, switch to SageMaker, where we have hyperpods, or other tools like SageMaker endpoints for a more managed experience. Then as you move down, you have storage. We know data is so important for AI. The storage that we have available here, ranging from Amazon S3 to FSX, which is a high-performance option for using on training data as you're feeding that compute. And at the bottom, which is absolutely critical, is networking, where we built Elastic Fabric Adapter, which is a low latency, low jitter communication protocol, communication between your nodes. And when you take those and then you combine all of these clusters together, we have petabit scale fabrics with EC2 Ultra clusters. And all of this is what combines and helps power our broad portfolio of compute, where we feature AI chips from our own AWS AI chips, inference and Trainium, but also a broad range of NVIDIA GPUs. And so in order to drive that innovation all the way up the stack around the infrastructure, we decided a while ago that we needed to develop our own silicon to address the cost effectiveness and the performance that you all wanted. So similar to Graviton with general purpose computing, we designed inference and Trainium. And so with inference and Trainium, we launched our first instance Inf1 in 2019. And we've been delivering AWS AI chips since. We released Tier 1 and Inf2 for both training and inference. And the most recent announcement of Trainium2, which we're really excited about, which will deliver some really optimized performance results. And we'll also have Ron come up on stage and do a deep dive. But the fundamental reason behind why we design our own silicon is it provides us flexibility to deliver more performance, lower costs, and better power efficiency. But it also allows us to control the supply chain so that we can innovate faster for you all. And AWS AI chips have been powering AI innovation at Amazon for a while now. Whether that's Alexa using their text-to-speech model running on Inf1, or all the way through to the recent announcement with Rufus, an AI shopping assistant that was launched for Prime Day, one of the largest ever, running on 80,000 inference and Trainium chips. But it's not just innovation at Amazon. We also see a wide range of customers using our AI chips. Some of them are displayed here. You heard some of them on the keynotes throughout the week. And we're really excited about the opportunity to offer these customers both more performance, but also lower costs. With customers like Poolside seeing up to 40% better price performance running on Trainium instances over comparable GPU instances. But we know the AI innovation is only getting started. And so as AI model capabilities continue to grow and we see them scale, whether it's through scaling or post-training, we're excited about the innovations that you all will bring. And so as you see here, I think most of us have seen some version of this graph now where you see exponential compute growing. But as a refresher, let's just take a look at why it's so important that scaling has continued. Well, first, scale improves with overall intelligence. So that means when you look at, as you start to grow that model size, and you look at the benchmarks and the scores on those benchmarks, you see improved performance results across those benchmarks. The second one, scale unlocks new capabilities. So again, as you start to grow both the data and the parameters, you start to see new tasks, the model capable of completing new tasks, whether that's things like arithmetic or physics or even reasoning. And then the third one, and this one's important, is that there's a predictable improvement in loss through scaling. So what that means is you can predict the loss you're going to get as you scale parameters, data sets, and compute. And so let's just take a closer look at that last one. So here we have the neural scaling laws from the original paper. And a shout out to James, who's part of the team, who works with part of the team that actually wrote this paper. And what we have here on the left, it was probably pretty clear. Parameter size are growing. So that's the leftmost chart here. But what's also important is that the data needs to grow in parallel. And you'll see here the data improves and the loss improves as you grow that data. But the one that I want to key in on is the one all the way on the right here, which is compute. So part of those scaling laws also showed that as you scale compute, you can reduce your accuracy. And so there's two takeaways, really. One is that these are empirical laws, and they've been tested across 8 orders of magnitude of compute. So when there are a few things, it's rare to have something that's not a natural law, to have that level of scaling to occur continuously over that magnitude. And then the second one is that these are power law scaling. And so you have on the slide here, the 1.5x improvement in accuracy requires 10,000 times more compute. So to keep continuing accuracy, it's exponential. You will need more and more compute. And so what we've seen across the notable AI models, as you can see here, is they've continued to grow in the amount of training compute. So you have the amount of training compute on the y-axis here. And so over the last decade, now models have reached up to 10 to the 25th flops of training compute. To put that in perspective, that's 16,000 H100 GPUs training for 70 days. And so to continue these scaling trends, and deploy the next phase of AI and structure, we think that will be in this quadrant. And to solve that problem, we're super excited to announce Trainium2 instances. So with Trainium2 instances, we're offering 30% more compute and 25% more HBM than the next most powerful EC2 instance, and that's at a lower price. We also deploy these in our Ultra Cluster Fabric, as I mentioned before, which gets you up to 60,000 chips in a non-blocking petabit scale fabric. All of this combined, you can run trillion-plus parameter models for training and for inference. So let's take a little bit closer look at the actual server and instance design. So first, you have 16 Trainium2 chips within a server. And when you package all 16 together, you get an aggregate of 1.5 terabits of HBM, high bandwidth memory, with an aggregate of 46 terabits per second of high bandwidth memory bandwidth. And Ron will go into this in a lot more detail soon. But holistically, what that means is Trainium2 instances, TRN2 instances, will offer 30 to 40% better price performance than other comparable EC2 instances, GPU-based EC2 instances. And so what do you think you do when you have the most compute and the most chip memory in a single instance? Well, you partner with one of the leading AI labs in Anthropic to build a massive Trainium2 cluster, aka Project Rainier. So Project Rainier is hundreds of thousands of AWS Trainium2 chips with hundreds of exaflops in a single training cluster. Now that is 5 times larger than Anthropic's previous training cluster. And so adding this all up and building this and planning for a cluster this large requires significant planning, both on the compute and also on the data science. But to start, I'd like to welcome up Ron to talk a little bit how we think about building silicon. Thanks. Yeah.
Thanks, Joe. And folks, thanks again for being with us today. For the next part of the talk, I'd like to tell you a bit more about how we built the Trainium2 devices. We designed Trainium2 around 5 main pillars: high performance, cost efficiency, scalability, ease of use, and innovation. Joe mentioned before that the scaling laws suggest that we need to invest vast amount of compute in order to train the next generation of state-of-the-art models. So let's start with performance. The first thing that we need to identify is what drives performance. And the first metric that might come to mind for most of you is TFLOPS, or tera floating point operations per second. That's true for some workloads, but not always. So let's use an example. When you interact with a chatbot, you typically type your input commands into a prompt, and then the first thing that the model does is to process the input prompt. This part of the computation ends up being quite compute-bound, and as a result, TFLOPS is indeed what drives performance. You can think about it intuitively as follows. We need to read all the model parameters from the HBM main memory, but then we get to amortize these read bytes over lots of computations. The amount of calculation is dependent on the size of the input prompt. The larger the input prompt is, the more we get to reuse the data read from memory. So for this portion of the workload, TFLOPS indeed drives performance. But that's not the whole story. After the model finishes processing the input prompt, it starts generating output tokens one after the other. And this portion of the workload ends up being very memory bandwidth intensive. And the same intuition that we used before still holds. We still need to read all the model parameters from the HBM main memory, but this time we only get to amortize the read bytes over the computation required to generate a single output token. So in some cases, memory bandwidth is what drives performance. But we're not done. There are cases where memory capacity is what drives performance. And a good example for this is model training with pipeline parallelism. The more memory capacity we have, the less pipeline parallelism stages that we will need to deploy, and that will improve performance. On the screen, you can see 2 examples. One is with a pipeline depth of 3, and the second one at the bottom is a pipeline depth of 2. And as you can see very clearly, with this lower pipeline depth of 2, the amount of idle slots reduces and the overall performance increases. We're still not done. In some cases, the interconnect is what drives performance. As Joe mentioned before, we're planning to do the next generation of state-of-the-art model training on clusters of hundreds of thousands of devices. And for that, we need a highly scalable fabric. That's exactly why we built the latest generation of the Ultra Cluster Fabric, which we internally, the engineers, call the 10P10U network. Let me tell you a little bit about the name, because I think it's quite revealing. The 10P portion of the name stands for our ability to connect thousands of servers with tens of petabits per second of non-blocking network bandwidth. And the 10U portion of the name means that any 2 servers can communicate with one another at under 10 microseconds of latency. So we built Trainium2 to provide leading performance across all the dimensions that we just covered. It comes with 1.3 petaflops of dense compute, more than 5 petaflops of sparse compute. We'll talk more about it soon. And it comes with 96 gigabytes of HBM capacity, as well as 2.9 terabytes per second of memory bandwidth. And as a result, the Trainium2 server, which is powered by 16 Trainium2 devices, is the most powerful machine learning compute server that we've built to date. It comes with 20 petaflops of dense compute, 46 terabytes per second of HBM bandwidth, and in terms of connectivity, it comes with 1 terabyte of neural link bandwidth that allows us to interconnect the different Trainium devices within a server, as well as 3.2 terabit per second of EFAv3 network bandwidth, which allows us to connect the different servers to one another via the 10P10U network that we just discussed. Let's look at some benchmarks. Here we can see the inference performance of a Llama 405B model. This benchmark was done by artificial analysis, and they measured the total response time for typical traffic patterns with 10,000 input tokens and 100 output tokens. We're measuring total response time here, so the lower the better. And on the left side, you can see the Amazon latency-optimized offering, which is faster than any other available offering in the market and powered by Trainium2. Here's another example. Here we trained the open source Fuji 70B model by Apple. We trained it on a cluster of 64 Trainium2 nodes. And we achieved 1.5x faster time to train and 1.7x lower cost to train compared to training on a similarly sized P5 cluster based on GPUs. So I hope it's coming across that the Trainium2 servers are quite powerful machines. But we didn't stop there. We also built the scale-up Trainium2 Ultra server. These are 2 racks connected together. You can actually see them on the expo, with 64 Trainium2 devices that are tightly integrated via the neural link fabric. This is a beast. It basically gives you 4x performance across all the dimensions that we discussed before. It's 80 petaflops of dense compute and an astonishing 185 terabyte per second of memory bandwidth. The Ultra servers will be key to training the next generation of foundation models. While performance is incredibly important when we train on hundreds of thousands of devices, we also need to make sure that we deliver this performance in a sustainable and cost-efficient manner. So let's talk cost efficiency. Machine learning workloads perform massive amount of linear algebra calculations. So we built Trainium2 around a highly efficient matrix engine that utilizes a systolic array structure. Systolic arrays are basically a grid of simple processing elements that perform simple operations like multiply and add, and then they pass data to their nearest neighbors. And systolic arrays are highly energy efficient because they provide with 3 main benefits. The first one is parallel processing. You can see on the screen that we have many processing elements that are performing calculations simultaneously. The second benefit is local communication. each processing element only communicates with its nearest neighbors, so we avoid long wires and communication over long distances. And the third benefit is data reuse. And data enters the systolic array on the left and then gets reused a lot of times before leaving the systolic array on the right. This allows us to amortize the cost of reading from memory and writing to memory over lots of compute. But if you've been following us for a while, you probably know that we already had systolic arrays in Trainium1. So let me tell you about what's new in Trainium2. In Trainium2, we further optimize our energy efficiency by moving from a lateral power delivery to a vertical power delivery. To give you a compare point, here on the screen you can see Trainium1. In green, you can see the voltage regulators, and they're placed at the top side of the card on both sides of the Trainium1 chip. We place them as close as possible to minimize the distance between the voltage regulators and the chip. And here's Trainium2. The voltage regulators are moved from the top of the card to the bottom of the card, and they're placed just underneath the Trainium2 chip. This shorter distance between the voltage regulator and the chip allows us to lower the impedance of the power supply network and improves our overall power integrity. Let's see it in action. Here we measure the voltage regulator's response to a burst of computation on both Trainium1 in purple and Trainium2 in green. When an AI chip starts a burst of computation, it draws a lot of power very quickly, which can lead to small drops in the supplied voltage. And this is pretty similar to what you see in your home sometimes, when the lights might dim for just a quick moment when you plug in a very powerful electrical appliance. If you look carefully, you'll see that the Trainium2 voltage drops are much lower than the Trainium1 voltage drops. And this allows us to operate Trainium2 at a lower nominal voltage, which improves its energy efficiency. And as always, what we do with that is to pass the corresponding cost savings back to you. Nice, so we talked about performance, we talked about energy and cost efficiency. Now let's move to talk about the scalability pillar. Deep learning workloads are very different from almost any other workload we've seen to date. On the screen, you can see a typical adoption curve for a new technology. And you can see that it starts relatively slow with early adopters, and then it starts to pick up pace over time. But with deep learning, that's not the case. As soon as we introduce a new technology, we get an immediate demand to build very large clusters of this new technology that we just introduced. And to meet this demand, we had to make sure that the Trainium2 servers are simple, modular, and robust. Here you can see a top view of a single Trainium2 server compute tray. The first thing that you might notice is that the design is quite minimalistic. There's not a lot of components here. The second thing that you'll notice is that there are 0 cables, and that helps a lot with robustness and scalability. And the third thing to notice is that at the back of the compute tray, there's a single row of 2 Trainium2 devices. And this single row of devices makes the cooling solution much simpler, which means that we can deploy with either liquid or air cooling, and that simplifies deployment at scale quite a lot. We also work to automate the majority of the assembly process. This includes things like torquing of the baseboard and also insertions of the DIMMs, the memories. And this high level of automation allows us to achieve very high server yields, and it also allows us to scale up the manufacturing lines very quickly. This combination of a simple and robust design, along with high level of automation, as well as AWS's experience in building large data centers, is what allows us to build clusters of hundreds of thousands of devices in a short period of time. Let's pause for a little bit. We talked about the hardware. We talked about how we deploy that hardware at scale. Now let's pop up the stack and talk about the software and the application layer. Trainium comes with the Neuron SDK. And the Neuron SDK is built out of 3 main components: a runtime, a compiler, and a set of developer tools. The runtime is the lowest level of the stack, which interacts directly with the devices. It boots the device, it loads a model into the device, submits inputs, collects outputs. The compiler gives us automatic code optimizations and performance optimizations to the training device. And the developer tools give us monitoring abilities, diagnostics, and profiling capabilities. We work very closely with the PyTorch and JAX teams, and we constantly contribute to the OpenXLA project in order to make sure that you can start from your framework of choice and seamlessly target training devices. To support distributed training and inference, we offer the NeuronX distributed library, or NXD for short, which allows you to shard your model over any number of training devices with just a few lines of code. NXD supports all popular forms of parallelism, including tensor and pipeline parallelism, expert, and data parallelism. Neuron also provides integration with a various amount of AWS services, as well as a variety of third-party libraries and frameworks. Hugging Face, for example, introduced the Optimum Neuron library, which connects between the Transformer library and the Neuron SDK. And what this allows you to do is to download one of thousands of models from the Hugging Face website and get started with Trainium with just a few clicks. Neuron also integrates with scale-up libraries, including and services by AWS, including ECS, EKS, and SageMaker, which makes your path to large-scale deployment much quicker. These various integrations allows you to get started with Trainium very quickly, and it also allows you to leverage your already existing code from other platforms. Last but not least, let's talk about innovation. Deep learning is moving at an extremely rapid pace, so it was critical for us to make sure that you're fully unblocked to innovate on top of Trainium. To start this part of the discussion, let's talk about a unique capability available in Trainium2, and that's sparsity. More significantly, 4x sparsity speedups. Trainium2 is capable of taking sparse matrix multiplications and accelerate them by up to 4x. We do that by compressing sparse matrices into a dense representation and then skipping the zeros during calculations. This is called K to N sparsity, and Trainium2 comes with a variety of supported formats, including 4 to 8 sparsity, 4 to 12 sparsity, and 4 to 16 sparsity. The notation here is that 4 to 16 sparsity means that we have 4 non-zero elements out of every 16 elements, and that's how we get the 4x speedups. An interesting point to note here is that other hardware in the market currently supports only 2 to 4 sparsity, so there is an opportunity here to unlock new science experimentation and see whether these new sparsity formats provide with significant gains over existing capabilities. When our team started to explore this new capability, the first question that came to mind is whether 4 to 8 sparsity provides a benefit over 2 to 4 sparsity. So if you look carefully, 4 to 8 sparsity and 2 to 4 sparsity both encode a 2x speed-up opportunity. But 4 to 8 sparsity gives you more flexibility in the sparsity patterns. The rightmost column here is not a 2 to 4 sparsity pattern, but it is a 4 to 8 sparsity pattern. So we took a llama model, in this case, llama 8B model, and we sparsified it to 2 to 4 sparsity pattern in green and to 4 to 8 sparsity pattern in yellow. We did it with 3 different techniques. We used Wanda, which is widely available and quite popular, and we also used 2 internally developed techniques, which we'll be sharing more in the next couple of months. What we've seen was very consistent. Across all these techniques, 4 to 8 sparsity provided superior accuracy compared to 2 to 4 sparsity. So that was encouraging, and the next step was to try to understand whether we can fully match the original dense model quality. So what we did here is that we took 2 models, llama 3 8B and llama 3 70B, and we sparsified them to 4 to 8 sparsity with various techniques, And then we compared the quality or the accuracy of the model compared to the original dense model. And what we've seen is that we were able to completely recover the dense original model in terms of quality. This is quite a powerful result. It means that you can leverage sparsity to speed up your models by 2x in the case of 4 to 8 sparsity without sacrificing the quality of the model. Now let's move to a different form of sparsity, a much coarser grain one. It's called mixture of experts. The idea here is that we take a transformer layer and we replace the second half of a transformer layer, called a feed-forward network, or FFN for short, with a set of smaller FFNs. We call these smaller FFNs experts. And then for each token, we choose to route them only to one, we choose to route that token to only one of the experts. So if you see here, I have 9 tokens on this slide, and each token will be forwarded or routed to one of the experts. This is exactly the reason that mixture of experts is quite compelling. It allows us to increase the number of parameters of the model and thus make it more intelligent without increasing the corresponding amount of compute that we need to train the model, because each token is only processed by a portion of the FFN. But like many things in life, mixture of expert comes with some constraints. In a perfect world, each expert will process the same number of tokens. Or said differently, the tokens would be uniformly distributed across all the experts. This would lead to a very regular and structured computation pattern that is easy for hardware to accelerate. But in real life, that's not the case. Some experts might need to process more tokens than others. So in order to make sure that Trainium2 is especially optimized for mixture of expert types models, we optimized dynamic memory addressing in Trainium2 and made it as efficient as static memory addressing. This allows us to dynamically pick the relevant expert for each token with minimum amount of overhead. Another thing that we did here is to build a highly optimized block-sparse computation kernel that implements the compute structure that I showed you in the previous slide. And this leads me to the next topic that I wanted to share with you. Basically, how do we write highly optimized kernels for training? For that, we launched the Neuron Kernel Interface, NKI. We like to call it NIKI. And NIKI is a bare metal programming environment for programming Trainium devices. NIKI allows you to bypass the compiler and integrate at the very end near the hardware, take full control over the hardware, and basically highly optimize whatever workload you end up working on. We use NIKI for 3 main use cases. In some cases, we try to invent a new operator that the compiler is not yet aware of. In other cases, we analyze a workload, we identify a bottleneck, and we want to super optimize that part of the workload. And the third case is quite unique, where we want to take full control of the hardware and use it in non-standard ways, very unique ways. Let's spend a minute to design our first NIKI kernel. This is sort of the hello world in NIKI. In the first line there, we define a NIKI kernel. In this case, it will be a very simple kernel that adds 2 tensors with one another. The next step is to load both input tensors, A and B, from the HBM main memory and move them into the on-chip memory. After that, we have a simple line that just adds 2 tensors together. We use the vector engine in order to do that. And finally, we take the data from the on-chip memory and write it back to the HBM main memory. One thing I'd like you to pay attention to here is that this elusively simple line, C equals A plus B, actually adds 2 tensors with one another in a fully parallelized manner. This is not adding 2 elements together, but rather adding, in this case, 2 128 by 512 elements to one another, parallelized across all the available computing resources. Now that we're all NIKI programmers, I'd like to give you an example of a cool example that our sister team here at Amazon did. They worked on a state space model called Mamba 2, And state space models are an alternative architecture, neural network architecture, to the transformer architecture, which are especially suitable to treating very large sequences, up to millions of tokens. But state space models are intrinsically sequential, which means that they require careful optimization to reach high performance. The team identified the kernel that is the bottleneck for their Mamba 2 model, and they wrote a Nikki kernel for it. And the results are quite cool. 18x speed up for that kernel in only 77 lines of Nikki code. If you'd like to learn more about it, you can visit the QR code on the top right. When you're building highly optimized code, what you really want is full observability. You want to know what the hardware is doing, what every engine is doing actually, and where the bottlenecks are so that you can know where to focus on and what to optimize. For that, your best friend is the neuron profiler. It's a non-intrusive instruction-level trace that gives you a full layout or a full trace of what your workload was doing on the hardware. Unlike other traces, the neuron profiler has very little overhead. In most cases, when you enable a trace, the trace itself has overheads, then the entire execution slows down, and that makes optimization quite challenging because the act of measuring the workload changed and shifted the bottlenecks around. So that's why we're very happy that the neuron profiler has absolutely negligible overheads. In fact, the overheads are so low that we typically just run with the neuron profiler enabled, just in case we want to optimize that workload later on. I have another interesting data point here. As you can see on the right, our profiler is quite snappy and interactive. And that's not a trivial task because we're processing vast amount of data here, every single instruction that ran on the hardware for a specific workload. This interactiveness is enabled by using a highly optimized algorithm, querying algorithm, for querying trace databases. Interestingly, this algorithm was invented by our friend Tristan at Anthropic. And the two teams actually worked together quite a lot on the neuron profiler to get it to where you can see on the screen now. One of the parts that I like the most about my job is to see everything that we just talked about coming together, and then customers are using all these capabilities to run end-to-end workloads and applications. Here you can see one customer running a Lava workload. This is an image understanding workload when we submit or input an image into the neural network and we get a description of the image as a result. This is the opposite case, a diffusion model for generating images. This specific model is called PixArt. And here we prompted the model with a request. Please give us an image of a blue jay standing on a large basket of rainbow macaroons. And we made the model kind of generate images as it was training. And you can see how the image quality improves over time until the very end after fine-tuning, where the image is really great and really nice looking. Now let's talk about our partnership with Anthropic. We're extremely fortunate to work with one of the best AI labs in the world, Anthropic. This partnership was amazing. We're benefiting a lot and mutually working to build the next generation of foundation models. So for the next part of the talk, I'd like to invite my dear friend, James Bradbury. He's a distinguished engineer at Anthropic, and he'll tell you about what we're building together.
Thank you so much, Ron. So at Anthropic, we make trustworthy AI. We do industry-leading fundamental research in both capabilities, making models better, and safety. And we build Claude, which is one of the world's frontier LLM families. We make it available, among others, through Amazon Bedrock. I am on the compute team, so part of my responsibility is planning and structuring the computational infrastructure that powers our training, our inference, our research, everything we do. And I'm always looking for the most cost-effective, most scalable compute platforms in the world for us to use in all of our work. Earlier this week, my colleague Tom was on stage at Peter DeSantis' keynote, and he announced that we're betting big on Trainium, especially Trainium2. We're using Trainium2 for fast, low latency Claude inference, and we're working with AWS on a truly massive new Trainium2 training cluster called Project Rainier. I wanted to explain in a little bit more detail basically why we made that choice, why we're betting on Trainium. So first and foremost, we're looking for the best price performance at the largest scale. Those are the core goals that we care the most about. And Trainium2 gives us great performance per dollar, especially on memory bandwidth bound or memory bandwidth sensitive workloads. And then on the scale side, we can rely on AWS for their world-class data center infrastructure experience. Really, they've built this for larger scale than anyone, and their expertise in large-scale capacity delivery. This kind of cluster is not routine for anyone, but it's the closest to routine for Amazon. And then we've learned a lot about the Trainium chip architecture over the last year or so, and really appreciate the flexibility, the programmability of all of the hardware engines in the neuron core. And then we can write low-level kernels that basically pipeline workloads across the different engines to absolutely maximize tensor utilization, squeeze out the most performance we possibly can. And then we can use the neuron profiler that Ron demoed to see exactly what instructions execute when and where on the chip. Almost no other accelerator can do that. And that really gives us the tools that we need to optimize all of our workloads. Oops. Oh no. So then the last thing is that we're incredibly excited about the ultra server architecture and scaling out to to support more kinds of parallelism on larger and larger models, both for LLM inference and LLM training. I think that the combination of ultra servers with Neuron Link and very large scale, high bandwidth, low latency EFA, the 10P10U, this combines for just really exceptional, smooth scalability up to very, very large training and inference workloads. And then last but not least, we're just incredibly appreciative of the phenomenal collaboration that we have with Ron and the Annapurna team, with Joe and the EC2 team, just everyone that we've worked with at AWS on everything Trainium. So Ron talked about clusters of hundreds of thousands of Trainium2 chips, and Tom talked about Project Rainier. What is it going to take for us to train at anything close to this scale? That's something we've thought a lot about, something we're spending a lot of time on. We need innovation at every level of the stack. And really, our team is already working hard on different aspects of what it will take to scale to Project Rainier. So ultra servers and EFA enable different new approaches to parallelism, and we want to really optimize what's the best way to take advantage of all of these different kinds of parallelism, the different kinds of network in the cluster. And then the Trainium architecture, the neuron core engines, and tools like Nikki and the neuron profiler, they enable us to squeeze almost every last flop out of the chip and the system. And we're going to need to do this because there's new bottlenecks at every scale, and we need to sort of constantly be profiling and optimizing and trying to figure out what the next how to unblock the next bottleneck, unblock the next scale up. And then on the other side, we need corresponding amount of work on basically reliability and testing. Large-scale, innovative reliability and testing infrastructure, because there's inevitably going to be hardware and system failures, and when you multiply them by the size of this cluster, they'll happen very often, and then we need to figure out how to adapt to them. And it's a new chip at unprecedented scale, so I think we're quite optimistic, but there's going to be problems we couldn't even imagine. But you know what? This is our favorite kind of challenge at Anthropic. We really like working at unprecedented scale. We have a phenomenal team dedicated to every aspect of this. And it's just this is what our company is built for. And then today, you can already use the first result of our Trainium2 work, which is a latency-optimized implementation of Claude 3.5 Haiku on Bedrock. So it's up to 60% faster for both inputs and outputs than the standard Claude 3.5 Haiku on Bedrock. And that means up to, depending on the prompt distribution, up to 125 output tokens per second. We're really excited to bring Trainium2 inference and lower latency to more models soon as well. Just for this demo, we hooked up Claude.ai to the latency-optimized Trainium2 Haiku 3.5. So we're going to show a little video of, I've created a Claude project that includes all of the NICI documentation. That means the programming guide, example kernels, architecture guides, everything that AWS and Anthropic have written about NICI and how to program in NICI. So we're going to try to teach Claude a new programming language, essentially, that it's never seen before because NICI is new. And we'll see how it goes. So let me get started. Yeah. So we loaded all of this into its context window. And we're going to ask Claude to write a kernel for softmax, and then explain each line in the kernel. So right now, it's going through processing and caching about 100,000 tokens of context on NICI. So all of these example kernels, et cetera. And that's going to take a few more seconds. OK, now it's done. It is generating code much faster than Sonnet 3.5 and other models. And you can barely keep up with how fast it's generating code. But maybe softmax is too easy. So now what I'm doing is I'm pasting a description of an activation function that Anthropic came up with and talked about in an old blog post, and asking it to write a kernel for that. So it's using a programming language it's never seen before to write a kernel that it's just learning about today. And I haven't gone through it super closely, but I think it's doing a pretty good job. The output is sort of coming out faster than we can keep up with. So I'll hand it back to Joe for last bit.
Thanks, James. And I just want to remind everybody, what we just saw was actually Trainium writing code to be used on Trainium. So super exciting stuff. And those are low-level kernels, so that's not something that's easy to do. And so really excited about the opportunity to partner with Anthropic. Really excited about all the innovations that we have that Ron covered earlier. But if there's 3 things that I want you to walk away with today, they have them right here. The first, Trainium2 is available today. We launched it in Matt's keynote. The second is that what we're doing with TRN is all around driving innovation for performance, energy efficiency, and cost efficiency. And then the third one is, hopefully made it evident with our partnership with Anthropic, along with the other innovations that we brought on Trainium2, that we're driving the next layer of technological foundation for frontier models. So that's all the way from the chips all the way up through the data science. And so if you want to get started now, we have a link here. We'll get you to the Neuron documentation. Feel free to scan that. And then if you're interested in learning more directly, we also have a few more sessions. There's a few more workshops available, so recommend checking them out as well. And there's a link to the blog post down here, which has all of those sessions, so you don't have to look them up yourselves. So with that, I just want to thank everyone. Thank Ron. Thanks, James, for coming up and talking about Trainium and Anthropic. And don't forget to fill out the survey at the end.